Hi Chem Peeps. In this video we're going to be talking about the ionization reactions for acids and bases. And so in the top right corner you can see I have some notes here that I've taken from my PowerPoint, and we need to talk about what a strong acid and a weak acid is versus what a strong base and a weak base would be. And so up here you can see that a strong acid is a strong electrolyte. Same thing with a strong base. A strong base is a strong electrolyte. So what does that mean? Well, it means it ionizes completely. We know ions are charged particles, and if we are going to ionize something, we need to know if it is a strong electrolyte or not. So here I have a flow chart where I have helped my students understand what a strong electrolyte and a weak electrolyte would be. A strong electrolyte, you can see at the top here, we're going to start with this first question. Is the compound water soluble? In other words, does it dissolve? Is it ionic? Okay, so ionic substances do dissolve for the most part. There is degrees of solubility, and so if it's soluble and it does dissolve, and you can look at your solubility rules chart, if it does, it's a strong electrolyte. If it does not, the next question is it an acid? If it's not ionic, is it an acid? Well, how do I know if something's an acid or not? An acid is going to start with a hydrogen in the formula. So, for example, hydrochloric acid or sulfuric acid. These are compounds. They're not ionic, but they do dissolve, and they do ionize. So, if it's a strong acid, it is going to be a strong electrolyte. If it is a weak acid, it's going to be a weak electrolyte. That means it only partially dissociates. And we're going to get into our acid-base chapter, but we need to understand the difference between a strong acid and a weak acid. Also, we have compounds that are covalent that do dissolve. For example, ammonia is basic. And if it dissolves and it's like ammonia or another molecular base, and a base is going to accept protons. In the traditional sense, it contains a hydroxide, an OH on it, but you can see right here ammonia does not have an OH. It is going to be more of your Bronsted-Lowry acid, where it accepts a proton. So it is weak, and if it does not have this basic nature, it is probably non-electrolyte. So this chart can help you a little bit. Another thing that I have my students do, especially in second year chem, and college chem and AP chem, is they need to memorize. I don't make memorization a requirement very often, but this is one of them. When you memorize the very short list here of what a strong acid and strong base is, you can see right here that we have about 7 strong acids. And to know them is to give yourself a step up in solving some of your acid-base problems. Your strong bases are going to be the ones from family 1 on your periodic table, and these 3 elements from family 2. Those are your strong bases. It's not a very long list, so it is worth memorizing. Okay, so let's talk about ionization. So I have 3 examples here that I'm going to do with you. I do want to quickly go back to these notes here. If it's weak, you can see that this HF is considered a weak acid. You can see that when it ionizes, it goes from its compound form to its ions. There's a double arrow here, meaning that it does not completely ionize. In other words, not every single molecule of acid breaks into ions. Only some of them do. A strong acid only has a single arrow. It completely ionizes. Every single molecule of HCl will break into its ions of hydrogen ion and chloride ion. Okay, and the same can be said of a base too. So let's look at this example. I have sulfuric acid, and sulfuric acid is on the strong acid list. So it is going to completely ionize. But you can see here there are 2 hydrogens. So there's actually 2 reactions. The first reaction only takes one of the hydrogens off. That is called the first ionization reaction. This, oops, forgot an H there. This reaction, or this acid, this first hydrogen, is considered to have a K of A that is very large. In other words, it completely dissociates. And I'm going to talk about K of A and K of B here in a minute when I open this chart. What's going to happen is that some of those HSO4 minus molecules will partially dissociate. In other words, I'm going to put a double arrow here, and it is going to take this. Some of the molecules are going to have the second hydrogen taken off, and that leaves behind some of the sulfates, but not every single one of them. And so if I open this chart, and I just got this chart off Google, but I am sure you have a chart similar to this in your textbook. So if we open this up a little bit more, sulfuric acid is right here on this chart. Okay, change my pen here. Sulfuric acid is right here, and you can see the K of A is large, meaning it completely dissociates. But if we come down just to here, this is the second molecule, the hydrogen with the sulfate ion. It has a K of A. It's 1.2 times 10 to the minus third. So I'm going to say the K of A here is 1.2 times 10 to the minus third. And you're like, what is that? Well, if substance has a K of A value, you're going to know it's weak. It's only going to partially dissociate. So let me quickly minimize this, and I will explain K of A here. So K of A is calculated by values of concentration in the equation. So the K of A is going to be the concentration of the products of the acid over the concentration of the reactant of the acid in the equation. So these little brackets here are concentration in molarity. So if I take the products of my K of A, and I have an acid, we're just going to generically call it HA, and it is partially dissociating. It's going to break into, some of it is going to break into hydrogen ions and a cation, or anion that is A minus. So the formula is going to be H plus times A minus, and those are concentrations of those all over HA. So in our example, this first one, it completely dissociates. So the concentration of the beginning substance is going to be the concentration of each of the ions. In other words, if this started out as 0.5 molar, this is going to be 0.5 molar, and this is going to be 0.5 molar. But in the second equation, we're taking this substance and only some of it dissociates. So the K of A for HSO4 minus is going to be the hydrogen ion in the second equation times the sulfate ion in the second equation all over the beginning substance, which is the hydrogen sulfite or sulfate formula. And we have a measured value. Every single time, 1.2 times 10 to the minus third is the value of products to reactants. Now, what's really important about this formula, which will come in further videos, is that this hydrogen concentration is used to measure the pH of a solution. So as we increase the concentration of hydrogen ions, the pH decreases. In other words, it becomes more acidic. Okay, and we'll do the same thing when we get down to the base. Okay, so let's go ahead and go to the second example I have here, acetic acid. We're going to write a formula for this, and this is considered a weak acid. So only some of the hydrogen ions dissociate, and only some of the acetate polyatomic ions dissociate from our beginning acid. And in fact, if I enlarge that chart, the K of A is going to be, for this formula, 1.8 times 10 to the minus 6. Now the one before was this one, 1.2 times 10 to the minus 3rd. This is larger, so it is a stronger acid than the acetic acid. So HSO4 minus is a stronger acid than acetic acid. And I can tell that because usually on these charts that I was using, they list them from strongest to weakest. So you can see up here we have the large, and then the values are just getting smaller and smaller, meaning that less and less of it is actually dissociating. Okay. All right, so let's look at the last one. The last one is ammonia. We talked about ammonia when we were talking about electrolytes. Ammonia in water is only going to partially dissociate. Okay, it is considered a weak base. So what's going to happen here is the water is going to react with the ammonia, and it's acting as a Bronsted-Lowry base by accepting a proton, and in this case a proton is a hydrogen ion, and it leaves behind the OH of the water. And if we look at K of B, that chart that I was enlarging actually has a KB value. The K of B value here is 1.8 times 10 to the minus 5th, which is actually a pretty weak base. So we talked about K of A up here, let's talk about K of B. It's very similar. It's going to be the product over the reactants, but it's going to be, so if we say K of B is going to be the base that has gained a proton, so it's going to be positive, all over the hydroxide ion. So these are our products, and I'll draw the equation here generically so you can see it, all over B. Now, so this is a very generic equation because what we use to represent that generic base is that a base in water is going to partially dissociate into BH plus and OH minus. And it's assumed that there's water here, and we don't have water in the formula because water, it has a value of 1, so it just falls out of the equation. But the base is accepting a hydrogen from the water, and it leaves behind the OH. Now, what we do is we use this concentration to solve for POH. And the higher the OH concentration, the higher the POH, which means it's more basic. So if I wrote the K of A, or I'm sorry, the K of B formula for this, K of NH3 is going to be the ammonium ion concentration times the hydroxide concentration all over the initial concentration of ammonia. And that would be our formula for ammonia's K of B. Okay, so we're delving into acids and bases. There's a lot to cover here. This is the initial lesson. You can find more as I roll them out on YouTube and TikTok at sChemChats. Leave me a comment if you have a question or this helped you, or leave me a like sign and share it with others. And I will see you on the next video.